Good evening, welcome back to AP Stats Notes Online. I want to continue talking about our inference procedures when we're interested in the difference in the proportions of two groups or two populations. We want to compare two groups or two populations, and again, it's very often that we want to do that. So we've covered the confidence intervals, and again, understand that what we're doing with the confidence interval is we're trying to come up with a set of plausible values for the difference in the proportions, of the true population proportions of our two groups or two populations, right? And so as we are concluding those intervals, we want to make sure that we talk about, we use language that talks about that difference. And of course, we have an example in the previous notes that sort of walk us through that. So, what we want to talk about now is trying to find significance, trying to find statistical significance that there is a difference in the true population proportions of two groups or two different populations. And so that's what a significance test is designed to do. Not to give us an idea of what that difference might be, but just to test to see if there's significance, if there's a significant difference in our population proportions. Okay? So the first thing we need to talk about is the only little additional spin on the idea of a test, a significance test for the difference in proportions. And it's the idea of pooled data or pooled sample proportion. Now, what are we talking about with pooled sample proportions? Well, where this comes from, right, is you have to remember what it is we're doing in a test, right? And so we're testing two hypotheses, right? And the null is always that statement of no difference. And so we can go back to the yawning situation, right? The proportion of people that yawn when they get a yawn seed versus the proportion of people that yawn without getting a yawn seed. Is there really a difference? Well, we always assume that there's no difference first. And so what we could do is something like proportion of yawn with seed. Well, let's go proportion of YS. And we're going to assume there's no difference in the proportion of people that yawn with a yawn seed versus the proportion of people that yawn with no yawn seed, right? And so we can write our null hypothesis in two different ways. We can do this, right, if the two proportions are exactly the same. Or we can actually write it visually seeing the difference. So if I subtract the piece of NYS from both sides, we could write it as the proportion, the P of YS minus the P of NYS, and that difference would be 0 if I just subtract that from both sides, right? So whether we understand that if there's no difference, then when we subtract those proportions, we're going to get 0, or if we're going to set them equal to each other, either one is fine. What we want to find evidence of is that the proportion of people that yawn with a yawn seed is actually greater than the proportion of people that yawn with no yawn seed. Or written another way, proportion of people with yawn seed minus the proportion of people yawn with no yawn seed is going to be greater than, if we subtract this from both sides, greater than 0. Is that difference positive? And if it is, then it lets us know that the proportion of people that yawn with a yawn seed, if the test shows significance, is significantly greater than the proportion of people that yawn with no yawn seed. So anyway, that's basically what our hypotheses are going to look like. Now, it's the idea of this pool of the sample proportion comes from this, comes from the null where we're assuming that there's no difference. Okay? The true population proportion for yawn with seed is no different than the true proportion of people who yawn with no seed. If that's the case, if we're going to assume there's no difference, and then that means that there's no difference in our two groups or our two populations. So what we do is, with that assumption in mind, we take our sample results and we just combine them. Okay? And so what we get is what's called a pooled sample proportion. And so it's a sample proportion that's obtained by combining our sample results, okay? And again, we do that, and as a parenthetical here, we do that because we assume there's no difference in our groups, which obviously there's not. Okay? Sorry, having some technical difficulties here. Because we assume no difference in our groups. Okay? That's why we do it. So, for example, we know that 4 out of the 16 that did not get a seed yawned, and then we know that of the 34 that got a seed, and now I'm trying to remember, it was 10, right? It was 10 that yawned. Well, if we assume there really is no difference, then we can combine these and get what's called a pooled proportion. And so our pooled proportion, or our combined proportion, is usually denoted as P sub C, is going to be equal to combining these guys. And so 10 plus 4 is your 14. And that's going to be divided by 50. Okay? Try a different board here. Having some pen issues. Okay? Now, why do we do that? Well, it's pretty simple, right? If we're assuming there's no difference in our population, then what do we know? We know that more information is better, right? So if we're assuming there's no difference in the proportion, then why don't we just combine our results, right? Because then we get more information that way. Instead of looking at each piece of information individually, if we combine them, then larger sample size always indicates more information and a better idea of what's going on. So that's why we do it. And we don't do it in confidence intervals because we're not making this assumption. We're not making the assumption that there's no difference. But since we are making that assumption with our tests, it makes sense for us to combine our data. Okay? So that's what we're going to do. Okay? So, how does that lead to our test statistic, right? Because what we know at this point from last chapter is that's the key, right? Our test statistic is what tells us, you know, if we see a difference in our sampling, where does that difference fall in our difference sampling distribution, and you know, what's the probability of getting that difference or a difference bigger than that just by random chance? And so, how does this pooled proportion affect our test statistic? Well, it affects it in the form of our standard deviation of our sampling distribution calculation, right? So our test statistic is going to be the same, right? I want to know our, and I'm going to leave this notation behind for now, right? And just talk about group 1 and group 2. So I want to know if there's a difference in my two sample groups, right? I'm going to take that difference and compare it to what I was assuming to be true, is that there's no difference, right? and I'm going to find out exactly how far away this actual sample difference was from what I assumed to be true, which was no difference. And I want to do that in terms of standard deviations, and so it would look something like this. We're going to use this idea of a pooled proportion. And again, we denote this as P sub C very often. And so it turns into P sub C times 1 minus P sub C all over the first sample size plus P sub C times 1 minus P sub C all over the second sample size. Now, what I hope you recognize is that this is the exact same formula, and it's derived from the exact same place as we did it for the confidence intervals. The only difference here is that instead of using our sample proportions, P1 hat and P2 hat, we're using the idea of this pooled proportion. And we just talked about why we're even talking about a pooled proportion. So your test statistic ends up looking something like this, right? That's going to become our z-score. That's going to let us know in terms of standard deviations how far away this difference is from our claim, and that'll lead to our p-value, which is the probability of getting that difference or a difference bigger than that just by random chance, okay? And that's the basis for our significance test. That's our only difference, okay? So what are the conditions for conducting a two-sample z-test for a difference in proportions? And that's what we're going to call it, is a two-sample z-test. Nice thing is they're the exact same conditions as the two-proportion z-interval, which should make sense because they were the exact same conditions that were from the one sample, only we have to make sure that we're checking, and I'm going to make this note here, check conditions for both groups. All right? All of our condition checks now should be for both groups. Okay? And we'll take a look at what that looks like in our next example. All right? So speaking of our next example, let's get to that. All right. Are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 1988 to 1994, 15% showed some hearing loss. In a similar study of 1,800 teenagers in 2005-2006, 19.5% showed some hearing loss. So these data are reported in the Arizona Daily Star back in 2010. Okay? So our questions. Do these data give convincing evidence that the proportion of all teens with hearing loss has increased? Well, first of all, look at your sample results, right? Does the sample results show a difference? Well, it was 19.5% in 2005-2006, where it was only 15% in 88 to 94. So the data does at least suggest that there's a difference. Now what we want to do is see if that difference is significant or not. Okay? Between the two studies, and so as a follow-up to this, between the two studies, Apple introduced the iPod. If the results of the test are statistically significant, can we blame iPods for the increased hearing loss in teenagers? And we'll tackle that issue in just a moment. Okay? And oh, by the way, if you don't think there's a relationship, you should take a stroll down the halls in between class and start counting the number of headsets that you can actually hear the music coming from. If you're wearing headphones or earbuds and someone else can hear your music, you're listening to it way too loud, and that is going to lead to hearing loss. Another good question for your anatomy or biology teachers. Okay, why that's the case. Anyway, let's go perform our test because it's asking, do these data give convincing evidence? And so we want to test and see if there's any sort of significance here in the sample results, right? So, again, in the state, plan, do, conclude format, here's what we want to do. First of all, since we're going to have P1s and P2s and P whatever all over the place, we have to define what each P represents, okay? And if nothing else, it'll give us a reason for our direction in our subtraction in just a few seconds. So P1 is the proportion of all teenagers with hearing loss in 2005 and 2006, and P2 is the proportion of all teenagers with hearing loss in 88 to 94. Okay, now you can obviously flip-flop those as long as you can keep track of what's going on. Okay, but that's one way to define those two P's. Now, we're going to test at a 5% significance level. Okay, and so now we need our hypotheses. And again, you can choose to write your hypotheses in two different ways. We're going to assume there's no difference. So if I was to subtract P2 from P1, that difference should be 0. Or we can write it in terms of P1 equaling P2. Either one is completely valid as far as a null hypothesis, right? What we're looking for is a difference that's not 0, and since we've defined this as 0506 compared to 88 to 94, then the P1 minus P2 would be positive. That's what we're looking for evidence of. Has the proportion of teenagers with hearing loss increased? And that increase would show up as a positive value when I subtract. Now, of course, you could always write it as, is P1 bigger than P2? That might make enough sense for some of you guys to do that as well. Okay, so we've got to make sure we show the world all of that. Okay, next, our plan. How are we going to do this? Well, we're going to perform a 2-sample z-test. Again, we have 2 samples from 2 different groups, and so we want to perform a 2-sample z-test. And we're going to test for P1 minus P2. That's our difference. Okay, only if conditions are met. And so our random condition, we've got to talk about the fact that both samples will come from random selections. Right, this says a study of 3,000 randomly selected teenagers here, and in a similar study suggests that they were randomly selected in the second study as well. So they came from separate random samples. Okay. For our normal check, now normally we have a claim to a proportion value that we can use in our to try to figure out the expected number of successes and failures in our sample. But we don't have a claim to that proportion value now. What we're claiming is that there's no difference between that there's no difference between 2 proportion values. So we do not have a P to use. So then, just as before, we have to default back to our P hats. And again, we're making sure we're checking both of these samples. So in the the 1988-1994 sample, 15% showed some hearing loss, so we're going to take 0.15 times 3,000 and 0.85 times 3,000 and find that both of those numbers of successes and failures are bigger than 10. Same thing with the 2005-6 sample, where the 0.195 times 1,800 and the 0.805 times 1,800 are both bigger than 10. So then we can safely assume that the sampling distributions for both groups, both populations, are approximately normal. Therefore, when we combine them into our difference sampling distribution, we can be safe in assuming that that's going to be approximately normal as well. Okay? And last but not least, we're taking a look at our independent condition. And again, we've got 2 samples, so we have to make sure that we're not sampling more than 10% out of either one of our populations. And so for 2005-2006, I think we can safely assume that there's more than 18,000 teenagers out there. And then in 1988 to 1994, we can safely assume that there are more than 30,000 teenagers that could have been sampled from. So both of those conditions are met, which means that our standard deviation calculations out of both of our populations are going to be fairly accurate calculations. Okay? So that being done, we're ready to perform our test. Okay? So we need a test statistic. And before we get our test statistic, we're going to pool our data. We're going to create this pooled proportion, or combined proportion. Again, why we do that is because we're assuming there's no difference between our 2 populations. And if there's no difference, then why not combine their data so that we have more data to look at one time, and should give us a clearer picture of what's going on. So we do need to show this calculation as part of our showing work. So make sure that you do include this somewhere. But anyway, so we're going to take our 450 successes from one group and the 351 successes from the other, and add those together, and then add our two sample sizes to create our brand new sample proportion that we're going to use in our calculations, the 0.167. Okay. Now we need our test statistic. What we need to know now is how different was this difference, right? So when we did this sampling, and we've got our sample proportions, then obviously there was a larger proportion of teens in 2005 and 6 that experienced hearing loss than there were in 98. Then there were from 88 to 94. So there was a difference. Now our question is, how different were they? And so we do this the way we've always done it in the past, and that is find the difference first, right? This 4%, 0.04, and I want to know how different is that than there being no difference. In other words, that when we subtract them, getting 0. So 4%, we're going to subtract 0 from it, right? That's going to tell us how far away 4% is from 0. And then we want to talk about how far away it is in terms of standard deviations. And so we do our standard deviation calculation, and we've taken a look at where that came from. The only difference now is instead of using P1 hat or P2 hat, we're using this PC hat, this combined proportion. And we're going to do this in both terms here, so the 0.167 and the 1 minus 0.167, but we're still going to divide by the individual sample sizes, as you see here. Right, so we're going to show our numbers being plugged in, and then our test statistic is 4.05. That tells us that this difference of 4% is more than 4 standard deviations larger than our claim of there being no difference. And what are the odds of that happening? What's the probability of getting a difference that is 4 standard deviations above the claim? Well, it's about 0. Now, you can plug this into normal CDF. You can go look at, you can try to find 4.05 in Table A, but you're not going to be able to. It's going to be off the table. So, and when we go over this, how to run a significance test in class through our calculator, we'll see that the calculator is going to give us a really small p-value there, a really small probability, right? And so we can just basically approximate it to 0. So what does that mean, right? It means that this difference is not likely to happen by random chance, and so we're ready to conclude. Since the p-value of, and that's blank, and I see. Since the p-value of about 0, that's what this is trying to say. Since the p-value of about 0 is less than 0.05, we're going to reject H0. Remember, the first sentence is always about what we're doing with H0. Are we rejecting it or are we failing to reject it? We're rejecting H0, and so the next sentence has to be all about what that means in context. So what that means is, if we're going to reject the claim of no difference, then that means we have convincing evidence that the proportion of all teens with hearing loss has increased. Right? We know it's increased because the 05-06 proportion was larger than the 88-94 proportion. And so the all teens with hearing loss has increased from 88 to 94 to 2005-2006. Right? So the next question, the follow-up question for this, part B, was can we blame it on the iPods, basically, right? Since Apple introduced the iPods in this time frame, does that mean that we can blame this all on the iPods? Well, to answer that question, does this test mention anything about iPods? Did we go sample from just iPod users? Did we randomly assign teens to listen to an iPod a bunch and then test them, right? And we didn't do that. So can this be blamed on the iPod? Not directly, not without more study, right? This is not a randomized experiment. There are definitely other possible reasons that teens have an increased hearing loss, right? And one of them could very well be, teens who listen to iPods probably also listen to music in their cars. It's been my experience, and I know statistics tells us not to rely on our own experience, but People that listen to their headphones and earbuds way too loud tend to listen to their music in their car way too loud. And so maybe it's the car stereos that are causing the hearing loss. Who knows? But it's not the iPods, at least not from this study. If you want to try to draw that conclusion, you'd have to set something else up to test it. Okay? All right. Anyway, there is your two-proportion z-test. And like I said, the nuts and bolts of it are pretty much the same. Couple of small changes, couple of small twists that we're going to have to make sure that we're keeping track of and that we're mindful of. Okay? We'll stop there for now and pick back up the notes the next night. Enjoy your evening. We'll see you guys in the next class period.